Hello, in this section I'm going to introduce the important idea of a term document matrix, but also I'm going to explain why it isn't actually a practical data structure for an information retrieval system. We'll take as our example doing information retrieval over the works of William Shakespeare. So let's suppose we have this concrete question: which plays of Shakespeare contain the words Brutus and Caesar, but not Calpurnia? Well, if you're starting from a very basic level of text searching commands, the first way that you'd think about to solve this problem is by using searching through the text of the documents exhaustively, what's known in the Unix world as grepping. And so we could kind of first of all grep for plays that contain Brutus and Caesar, and then if you know your grep command well, you can give a flag for files that do not match, and you could get out the ones that don't contain Calpurnia. Now, these days, for works of the size of William Shakespeare, for this kind of query, grepping is a perfectly satisfactory solution. Our disk drives and computers are sufficiently fast that you could use this method, and it takes no time at all to find the answer. But nevertheless, that isn't a good answer for the full information retrieval problem. It falls flat in a number of ways. Once your corpus becomes large, and so that means something like everything on your hard disk, or even more so the World Wide Web, we can't afford to do a linear scan through all our documents every time we have a query. Then some parts of it, like the not part, become less trivial to implement than just finding things. But even more so than the not part, we'll have more complex queries, like finding uses of the word Romans near countrymen, and we can't do that with a grep command. But even more than that, the big thing that's happened in information retrieval is the idea of ranking, finding the best documents to return for a query, and that's something that we just can't get out of the linear scan model of finding things that match. And we'll talk about all of these issues and the way they're handled in modern information retrieval systems in later lectures. But let's first go to this idea of a term document matrix. So what we do in a term document matrix is that we have the rows of the matrix are our words, or often they're also called in information retrieval the terms, and then the columns of the matrix are our documents. And what we're doing here is a very simple thing. We're simply saying, let's fill in every cell in this Boolean matrix by whether the word appears in the play or not. So Antony appears in Antony and Cleopatra, but Calpurnia does not appear in Antony and Cleopatra. So this matrix represents the appearance of words and documents. And if we have this matrix, it's straightforward to then answer Boolean queries, such as our example before. Queries for documents that contain Brutus and Caesar, but not Calpurnia. Let's just go through concretely how we do that. So what we're going to do is we're going to take the vectors for the terms in the query, and then we're going to put them together with Boolean operations. So first of all, we can take out the row that is referring to Brutus, which goes up here. Then we can take the row for Caesar and it there. And then finally, we can take the row for Calpurnia, complement it, and then stick it down here. So Calpurnia only appears in Julius Caesar, and so we've complemented it to a vector where everything is one apart from Julius Caesar. And at that point, we can just AND those three vectors together, and our answer is this one of 1, 0, 0, 1, 0, 0. And so we've been able to do information retrieval successfully and can tell that this query is satisfied by the documents Antony and Cleopatra and Hamlet. And indeed, we can then go off to the document collection and confirm that that is the case. So here we are. So in Antony and Cleopatra, when Antony found Julius Caesar dead, he cried almost to roaring, and he wept when at Philippi he found Brutus slain. And similarly, we find both words occurring in Hamlet. Okay, so that suggests that we could do information retrieval simply by working with this term document matrix. So an important thing to realize is that that doesn't really work once we go to sensible size collections. And so let's just go through that for a minute. Let's go through a sensible size but still small collection. So suppose that we have 1 million documents, and we'll often use n to refer to the number of documents, each of which is on average 1,000 words long. Okay, so what does that mean in terms of the size of our document collection and in terms of the size of our matrix? So if we have an average of 6 bytes per word, including spaces and punctuation, the amount of data we're talking about here is 6 gigabytes. So that's a teeny fraction of one modern hard disk in your laptop. But let us then suppose we try and work out how many distinct terms there are in our document collection. And we need to know the number of distinct terms because that corresponds to the number of columns in our matrix. And let's suppose there are about 500,000. That would be a typical number for 1 million documents. And so I'll often refer to this number of different terms as M. Well, what does that mean? Well, what it means is that even with that size document collection, we can't build this term document matrix because we'll have 500,000 rows and 1 million columns, and that's 500 billion zeros and ones. It's already huge and probably bigger than we have space to store. And as the document collection gets bigger than 1 million documents, things are just going to get worse. But there's this really important observation, which is although the matrix here had 500 billion zeros and ones in it, that actually almost all of the entries are 0, that the document has at most 1 billion ones. And it'd be good for you guys to stop and think for a fraction of a second, why is it that there are at most 1 billion ones? And the answer to that is, well, if we have 1 million documents and the average document is 1,000 words long, as we said last time, then the actual number of word tokens is only 1 billion. So even if we assume that every word in every document were different, we could only have at most 1 billion one entries. And most likely we have far less than that because we'll have common words like the, of, and to occurring many, many times in each document. And so therefore the key observation is the matrix we're dealing with is very, very, very sparse. And so the central question in the design of information retrieval data structures is taking advantage of that sparsity and coming up with a better data representation. And the secret of doing that and having an efficient storage mechanism is we want to only record the positions that hold a 1 and not the positions that hold a 0. Okay, so I hope that's given you an understanding of the term document matrix. It's an important conceptual data structure that we keep on coming back to again and again when we talk about various kinds of algorithms. We think about them in terms of that matrix, as you'll see. But when we actually come to doing storage in computer systems, we can also see that we never actually want to store documents and their information retrieval representation in that form.